All right, hello everyone. Uh, so, sorry, every once in a while my eyes will have to go to my email because I've been having computer issues. My brand new fancy MacBook Pro is now a paperweight that basically does nothing. So, yeah, won't turn on, won't do anything. Just blows out air every once in a while. It's fantastic. Of course, the keypad is now lighting up, which is kind of interesting, but nothing else will happen. So, but anyways, enough of my trials and tribulations. Anyways, so today in lab, we're going to be playing with Ohm's Law again, which is what we played with last time. So just to remind you, Ohm's Law says that if we have a battery hooked up to a resistor, then current will flow through our circuit. So basically, if we have no resistor, then we'll have no current, is basically what Ohm's Law says. So here says that Ohm's Law says that the potential supplied is equal to the current times the resistance. So if the current goes, well, let's say, so if the resistance goes up, the current will go down. If the resistance goes down, then the current will go up. So this is our simple circuit, where this little squiggly line here is what we call a resistor. So basically, again, for the same reason that we saw with capacitors, we can only manufacture so many different types of resistors. And then if we want to create new resistors, then we're going to have to combine these resistors together to then create different resistances. So just like we did with capacitors, the two different ways we can combine these are first in series, and then the second is in parallel. Go. So series, like we saw before, so series just basically means that, again, there is no way to get around these guys having current flow through each one. So this would be, say, something in series. So here I'd have R1, here I have R2, here I have R3 connected to my battery delta V. So again, this is in series because there is no branching points, there are no nodes, meaning that once the current comes out of the battery in this direction, my internet connector is unstable, great. Then all the current has to go through each one of these different resistors. It has no other choice, it has to go through those resistors. As opposed to, in this scenario, then I can have current go through this one, or current go through this one, or current go through this one. So this is what we call parallel. So parallel means that there are options, there are nodes. So as we talked about before, so this spot here is a node, and this spot here is also a node. So these are nodes, or again, branches. So my current has options to go different directions. So here, the current that comes out of the battery is then going to split. So some of it will go through here, so through R1. Some of it will go through here, so I2. And then some of it will come down through here, I3. Well, what has to be true is that all of these currents have to recombine back together into the same currents as they then go back through the rest of the circuit. So all that means then is that current I1, I2, and I3 all have to sum together to equal that original current I. So I then is going to be equal to I1 plus I2 plus then I3. So the idea, much like we did with capacitors, is we want to take this and combine everything here into a single resistor, and combine everything here into a single resistor so that we can redraw. So that now we have one single resistor attached to our battery. So this is then delta V with the amount of current I, which is what we call REQ, which is the equivalent resistor. This is the equivalent resistance. Equivalent resistance. So it turns out for series, the way that these guys sum together is that REQ is simply equal to the sum over all the resistances. So this is RI. And then when they're in parallel, the way we add them together is that we take 1 over the resistances and then sum those guys together. So 1 over the resistance then is equal to the 1 over the equivalent resistance. So notice when we look at these are actually the opposite of what we had for capacitors. So for capacitors, the way it worked was when they're in series, we added them inversely. And then when they were in parallel, we added them directly. So resistors are just opposite of that. So now when they're in series, we add them directly, which means that if we put them in series, the resistance goes up. But if we add them in parallel, the resistance then goes down. So when we add them in series, this then increases the resistance. And then when we add them in parallel, this then decreases the overall resistance. So this is the overall effect of it. Anyway, we'll talk more about this in class as well, but good. So let's work through kind of the example that's given in the lab. So let's bring up our lab. So here it says an example. So we want to know how much current is drawn from the battery, which is shown in this figure. And then what is the corresponding current through each of the different resistors? So basically what I want to know is, again, if I combine all three of these resistors, where these two are in parallel and this one is in series, so I want to combine all these down into an equivalent resistor to then determine the amount of current which is flowing through the circuit. And then break all that apart to then determine how much current is flowing through each one. Now, remember when we talked about with capacitors, certain things are the same. So with capacitors, what we said was in series, the charge was the same. But now since charge flowing as a function of time is current, what's the same in series then is current. So current is the same. So that means is that the current running through resistor 1 here is the same as current running through resistor 2, which is the same, which is flowing through resistor 3. So as long as these guys are connected in series, the currents then are the same. When they're in parallel, what's the same as the potential? So the potential across resistor 1 is the same as the potential across resistor 2, which is the same as across resistor 3. So let's kind of work on this example because this is what we're going to be doing in lab. So let's redraw our system here. So I have my battery, so delta V, attached then in series with resistor, let's call that R1, connected then in parallel with resistor R2, which is also in parallel with R3, which are then recombined together to then close our circuit. So again, what we want to know is what is the overall current running through our circuit? What is the current going through resistor 1? What's the current going through resistor 2? And what's the current going through resistor 3? So these are all the things that we want to know. Good. So good. So first things first is we're going to look and see that what? These two are actually connected in parallel. So these two resistors are in parallel. So the first thing we're going to want to do is redraw our circuit here to put those two things in parallel. So I'm going to redraw so that now I have R1 here connected now to an equivalent resistor, which we're going to call R23, which is R2 and R3 put together. And this is now our new circuit. Now, since R2 and R3 are in parallel, what that means then is R23 is going to be equal to R2 times R3 divided by R2 plus R3. So if I plug in my numbers according to what this thing says is that works out to be 290 ohms. So we'll use that here. So that's going to be 290 ohms. Good. So now what I can see is resistor 1 and resistor 2, 3 are now in series. Right? These are in series because, again, there's no junctions, there's no place for the current to go. It can only go directly through these two resistors. So these two guys are in series. So the way we combine in series, once we combine these guys together to now create our REQ. So now this is my new circuit. So delta V with REQ. So REQ then is going to be, because they're in series, we're simply going to add these two guys together. So it's going to be R1 plus R23. So R23 we now know is 290, R1 was 400, so that's going to give us 690 ohms. Good. So now, since we know the battery, we now know the equivalent resistance, we can now find the equivalent current. or we can just call that the current. So how much is the battery? So the battery is 120 volts. Okay. So the battery was 120 volts. So using Ohm's law, which again says that the change of potential is equal to the current times the resistance, this means our equivalent resistance then is going to be equal to the potential from the battery divided by Req. Okay. So it's going to be equal to 120 volts divided by 690 ohms, which works out, according to what we did here, to about 0.0174 amps. So this is 0.0174 amps. Okay. So now, from here, we have to work backwards. So from this picture, we're going to go backwards. What we now know is that the current which is running through here is 0.074 amps. And what we know is that Req came from two things which were connected in series. What we know is that what's in series has to have exactly the same current. So we know the current I1 here and the current I23 here are both exactly equal to our IEQ. So we know I1 is equal to I23, which is equal to 0.0174. So that means that I1 here is simply 0.0174. So that's the amount of amperage coming through that particular resistor. Now, we also know that the current going through R23 is also 0.0174 amps, but we know R23 came from two things which were in parallel, and we know that what's in parallel is the same is the potential. So now we have to use this current in this resistance to now determine the potential which is across that particular resistor. So using Ohm's law again, we know that the potential across resistor 2,3 is the same thing as the current, which is the equivalent current, times that resistance of R23. So that amount of potential, which again we calculate from over here, works out to be, where was that? 5 volts. Okay, so this is equal to 0.0174 times, what was that, 290 amps, which works out to be 5 volts. Is that right? That seems small. Let's check these numbers real quick. Where's my mathematical? There it is. Okay. Yeah, so let me check these numbers. They seem off. I would believe 50 volts. Might be 50 volts, but. My computer's been ridiculously slow all day today. Sorry. Let me use my phone. Oh, there we go. Okay. Good. So let me check that first number first. So it was 120 divided by 690, is that right? Good. So that is. Oh, sorry. Okay. So we shouldn't have the 0 here. So that should be 0.174, not 0.074. Okay. I'll have to change that. So this should actually be blue again. 0.74. Good. Which means that is also 0.74. And this is also 0.74. So 0.74, and then use red. So 0.174. Good. So 0.174 times 290 is 50.46. Okay. So this should be 50.46. Volts. Good. So good. So now that we know this has 50.46 volts, what we also know then is that what this and this, so meaning that R23 came from two resistors which were in parallel. We know what's the same in parallel is the voltage, which means that the amount of voltage across R2 is the same as the amount of voltage across R3, which is the same amount as R23. So the amount of voltage here is the same as here, which is the same as across those two combined together. So that means this also has 50.46 volts, and this also has 50.46 volts. Okay. So now that we know the voltage across here, we also know the resistance, we can now determine the current. So that current, I2, then is going to be equal to the potential, which is the 50.46, divided by that amount of resistance, which is 500. So now we're going to divide that by 500. And then this one is going to be equal to that 50.46 divided by 700, because that's the amount of resistance across there. So I2 then is going to be, let's do that, so it's 50.46 divided by 500. So that's 0.1, so 0.1009 amps. And then this one is 50.46 divided by 700, which is 0.072. We have 0.072 amps. Okay. So this is then the amount of current across each one. Okay. So this is basically what you're going to be doing in lab. So in lab, what we're going to have is then you're going to use the PHYS simulations, and we'll talk about the first part in a second. So let's talk about the second part. So in the second part, you're going to be building these two different circuits. So you're going to be building circuit number 1, or circuit A, and then circuit B. And then what you're going to be doing is measuring the potential across each one, as well as the current through each one. And then you're going to compare that to your theoretical result. So theoretically, you're going to take the numbers, you're going to combine everything down like we just did here, find the equivalent of resistance, from the equivalent of resistance, find the current, and then backtrack to then determine exactly what each one is. And then calculate the discrepancies and all that good stuff. And then in part 1, we're going to be doing what? We're going to connect a single resistor and then apply that then with a battery, which is then 3 volts. And then we're going to measure the current through that resistor, as well as the potential across it. And then we're going to do that with 6 volts, 9 volts, 12 volts, and 15 volts. And then you want to do an Excel plots of the potential versus the currents. Plot that, get a best fit line, and then the slope of that best fit line will be the resistance. So we're just going to basically measure and make sure that this thing is not lying to us. Okay, so let's build our PHYS simulation here. So basically what that means, we're going to take a battery, okay, and then I'm going to connect that to an ammeter. Okay, so here's my ammeter. I'm going to take some wire. Okay. And then I'm going to connect to that my resistor. Okay, so here's my resistor. And then I'm going to connect another piece of wire back to the battery. Okay. So first things first is you're going to set the potential to 3 volts. Let's put that at 3 volts. Good. And then we want to put this at 60. Okay. Good. So basically all you're going to do is in the first part, you're going to measure the current, which is basically just write this down, 0.05 amps, pull out your voltmeter, and then you're going to measure the potential across each one of these. Actually, let's put a little bit of resistivity in the wire. That'll be fun. Okay. Right, and then basically just measure that voltage. And then from there, we're going to increase the battery. So now put the battery at 6 volts. Again, do the same thing. Measure the potential across it, measure the current, and again, same thing. Change now to 9, and etc. And then from there, you're just going to do an Excel spreadsheet. So on your Excel spreadsheet, you want delta V on the y-axis, I across the x-axis, plot all your numbers, get a best fit line. That's then going to have a slope, which is going to be equal to the resistance. So basically, you're just going to compare this. What we know is this should be 60 ohms. You're just going to compare that to the 60 ohms. Okay, so this is part one. Yeah, part one. So part two, again, what you're going to do is build each one of those different circuits. So let's build one of those circuits together, just for fun. So let me restart all this. So let's do the first one. So again, you want to pull out your battery. So here's going to be my battery. We're then going to connect that in series to our first resistor. So let's put our first resistor. Rotate. There we go. Good stuff. Good. Now it's connected again to our second resistor. So let's put a second resistor in here. Now from here, if we go by, so here I'm building circuit A. So after there, we go into parallel. So the way we can create parallel from here is we can put one wire here and then put another wire here. Where'd you go? Put that there. Rotate this. And then put this wire here, okay? So what this does is it creates the junction right after the resistor, okay? So this is gonna put it in parallel. Now I'm gonna put another resistor here, and I wanna measure the ammeter, so let me put an ammeter here, and then I'll put another ammeter here, and I'm gonna put another wire, which is now going to connect here back to the battery, okay? So this is gonna be my situation. Actually, let me cut this here. Let's put an ammeter here. Great. Actually, I'm going to cut this one too. Let me put an ammeter here as well. Okay. Now from here, we have to set all of our information. So here, what it tells me is the battery is going to be 10 volts. So set up the battery for 10 volts. Good. The first resistor is at 15, and then 10 for the second one. So this one we're going to put at 15. This one's going to be at 10. Good. And then the third one is at 33, and then the fourth one is at 55. So we're going to put this one at 33. Good. And then this one finally at 55. There we go. Okay. Good. So basically, again, all you're going to do is you're going to measure the currents as this thing tells you from your ammeters. So for example, the current through resistor 1 is 0.21 amps. Current through resistor 2 is also 0.21 amps, as they should be because they're in series. Through resistor 3 is 0.13 amps, and then through resistor 4 is 0.08 amps. Then you're going to take your ammeter and then basically just measure the potential difference across each one of these resistors. So in this case, potential difference across this first one is 3.22, and then measure across this one. So that gives me, why am I getting 0? Oh, because I have a piece of wire in here that's not supposed to be here. There we go. Good. So that one then is 2.15, and then measure across this one. So this one then has 4.42, and then this one should also be at 4.42 since they're in parallel. It's slightly different, but that's fine. Probably because of the wires. Okay, so good. So that's it. So from here, you're going to measure these things, and then again, you're going to calculate them theoretically, and then compare those numbers to all of the theoretical amounts. So you should calculate the currents as well as the potentials across each one, and then compare both the calculated and theoretical currents as well as the calculated potentials and the theoretical potentials. Okay, so do that for the two different circuits. So in this case, for circuit A and for circuit B. Okay, and again, the difference between the two is that R1 and R2 are originally in series, connected in parallel with R3 and R4. And then in the second case, only R1 is in series, which is then connected in parallel with 2, 3, and 4. Okay. So that's it. So not too bad. Not too bad. So anybody have any questions on any of the stuff? You can leave off the internal resistance of the battery. Just keep that at 0. That's fine. You don't need to put anything else on there. But yeah. So any questions? Everybody's okay? Like I said, first part is mostly just verifying that the PhET simulation is not lying to you. Of course, there should be no reason why it is lying to you, but you never know. Everything's okay? Okay, well, if everybody's okay, then I will be here. So come on and ask questions if you have them. And yeah, otherwise I'll see everybody tomorrow.